Well, thank you very much. I should point out to those of you here up in the north of England that it's bright and sunny and there's not a trace of rain down in Cambridge. Well, why am I talking to you about maths and sport? Some of you may have heard the Olympic Games are being held in the United Kingdom, in London in 2012. And the Millennium Mathematics Project has been appointed, or whatever the right word would be, the official providers of mathematics and scientific education to accompany the cultural programme of the Olympic Games. When you sign the contract to hold the Olympic Games in your city, you are also legally obliged to provide a sort of cultural Olympiad and to provide educational activities associated with the Games, both nationally and internationally. And so I've given quite a lot of thought in recent times as to how one might use sport to interest students and young people in mathematics, and also how mathematics might show you something about sport that perhaps you didn't realise or understand before. As always, when one tries to persuade people why it's important to understand and study mathematics, the answer I usually give is simply that mathematics can tell you things about the world that you can't learn in any other way. So I'm going to pick a whole group of rather different types of topics in sport which have some unusual mathematical complexion. Some will be probabilistic, some will be mechanical, some will almost be number theoretic. So the first is a simple question that you might pose to people on this campus at random. Why do tightrope walkers carry long poles? Here's a rather extreme example. This is Philippe Petit walking between the two twin towers back in 1974. And you notice, like all the tightrope walkers you've ever seen, he carries a long pole. Okay? Why do tightrope walkers carry long poles? I even wandered around the Cambridge Mathematics department and asked this question 4 or 5 years ago, and I was surprised how many wrong answers I got. Lots of people think the answer is all about centre of gravity, and they very quickly say, oh, it lowers the centre of gravity of the tightrope walker, so he's more stable. If you think twice about it, you realise he actually raises the centre of gravity of the tightrope walker. So this is not about centre of gravity, it's about something a little bit different. It's about inertia. So, moment of inertia, you're a sixth former, studying further maths, you'll perhaps start to learn something in the mechanics options about inertia. If you haven't, inertia is simply the distribution of mass within an object. So what matters when you want to move something is not just its weight, but the distribution of that weight. And in particular, the moment of inertia tells you the extent to which the mass is distributed either in a concentrated way close to the centre or far from the centre of an object. So if you have a hollow shell or a ring, for example, all the mass is distributed far from the centre. If you have a disk or a uniform sphere, then the weight and the mass is distributed evenly throughout the sphere. If they're made out of different materials, so the densities are different, yet the mass and the diameter is the same, the object with the higher inertia, as the name suggests, will be the one which it is harder to move. That will move more slowly when you give it a push, when you spin it, when you roll it down a slope. So typically, dimensionally, the inertia looks like the mass of the object times the square of its radius times some concentration factor, a number of order unity that tells you how concentrated the mass distribution is around the centre. And if it is concentrated at the centre, the concentration factor is small. If it's far away, it's large. If we go back to our tightrope walker, we begin to see what's going on. By carrying a long pole, sometimes you might even see a mass at the end of the pole, what's happening is the tightrope walker is increasing their inertia. They're moving mass far away from the centre line of their body. And so when they wobble more slowly than they would without the pole, so they have more time to correct and get their footing right. So you can try this for yourself with a sort of ruler rather like this, that if you have a long one like this, you can see the period of oscillation is rather long, proportional to the square root of the inertia. If you did it with a pencil or something smaller, you would have a struggle to balance it because it would wobble rather too quickly for you to keep up with. Well, that's the simplest example of inertia that we see in not so much a sport, but more a sort of demonstration publicity event. But if we start to look for inertia in other sporting events, we begin to see the same type of effect being manifested. So here's Bradley Wiggins on the way to one of his 3 Olympic gold medals, and he rides a bike that's not like the bike that you and I ride around town or campus. We wouldn't last very long on this bike. The first time you tried to make a turn away from going straight forwards and there was any breeze in the air, you would end up on the floor. But velodrome type racing bikes, they have no brakes. The wheels are always kept perpendicular to the ground, even on the bend. And so you see the prevalence of these disc wheels. So why would you do that? The moment of inertia of a disc, you remember, is half ma squared. If you put all the mass into a ring, the moment of inertia is twice as big. It's ma squared. So basically by having a disc-like wheel, you lower the inertia, you get a quicker response if you drive on the pedals. If you want to cycle on a road race, of course, you're going to have the same problem that you and I have. So what you tend to see is this hybrid system with the low inertia wheel on the rear, but a rather more practical, transparent, partially transparent wheel on the front to let the airflow go through. If you look around other events, for example, running, if you watch a top-class middle-distance runner on the track, if you watch film of someone like Sebastian Coe, you'll find you tend to keep your arms rather high, like this. The reason for that, again, you're moving that body mass closer to the center, you're reducing your inertia. If you want to change balance, if you want to maneuver quickly from lane to lane or to move forward, you can do so with much less effort than if you were running with your arms down like that. If you look at cross-country runners, you'll find that they tend to run on an uneven surface with their arms much lower because they're interested in balance more than making small maneuvers. So they try to make their inertia rather bigger so that if they put their foot down a pothole or something, they don't so easily fall over and move. Well, motion doesn't only take place in one dimension as it appears to for a cyclist. And inertia is similar. If you have a 3-dimensional object, there are 3 different mass distributions. So for this little squash racket here, okay, we have 3 different axes about which we could rotate it. This vertical one, we could lay it flat on the ground, rotate it about that, or we could spin it around this central axis here. Now around each axis there is a different distribution of mass, and so there is a different inertia. And one of the great discoveries of Euler and the other applied mathematicians of that era was that if you rotate a body about any of those 3 axes of inertia, then the motion about the in-between axis of inertia, so the one that's neither the biggest nor the smallest, is unstable. So if I spin this about this axis, it will just spin. There's nothing exciting happening. Spin it about this axis, nothing exciting will happen. But if I spin it about this axis, so on this piece of paper it says up. If I throw it and catch it, up is now down. So this has done a twist as it's gone up. It's now back up. I won't do it again. But you see what's happened. There is an instability for rotation about that central moment of inertia. Now, if you're a gymnast, you would want to take advantage of that. If you look at pictures of gymnasts, one of the things that they try to do, divers also, is to change your body shape, to change the distribution of your body mass relative to your centre. And so if you're a little girl doing somersaults on the beam, you tend to get more points and more credit. Or if you're a gymnast on the floor, if you do a somersault with a twist. But you can see if you arrange your body mass distribution correctly, you can't avoid doing a twist. So you exploit this instability so that if I run along here and do a somersault sufficiently laid out, I will end up facing in that direction when I land. Whereas if I'm a highboard diver and I dive in a tuck position like that, I make sure that that forward rotation direction is not the intermediate moment of inertia, and I do not do a twist. In any situation where you're rotating, the conservation of angular momentum, as we appreciate quite well, determines the angular velocity at which you will rotate if your radius, if your extent is r. And the most common example, of course, is ice skaters starting spinning slowly and drawing their arms in. Angular momentum is roughly conserved, and they spin faster and faster and faster. But we see this elsewhere. We see it in divers, these Chinese divers here. As you approach the water, you will come out of that tuck position, increase your body height and extent, increase your inertia so that you rotate more slowly in the final phase when you enter the water, so that you can enter vertically and maximize your points and all that sort of thing. So all across these types of events where there's rotation, there is this play, this training that leads you to change and exploit different possible moments of inertia for your body mass distribution. Well, let's leave this sort of spinning stuff for a while and let's have a look at boat race type stuff. So just last weekend, I think the boat race took place. And here's a picture of typical configurations of rowers in a 4 and in an 8. And these configuration patterns are generally called rigs by people who row. And you can rig the boat however you wish. You don't have to go right, left, right, left, right, left, right, left. Okay, it's up to you how you rig the boat. You could have 4 people on the left-hand side, followed by 4 people on the right-hand side if you wanted. But this is the so-called standard or conventional rig that you will generally see used by oarsmen on the river. And a question that I asked myself about 18 months or so ago was, is this really the best configuration to use? Well, if you think about it, it has a rather funny property. There is a hidden asymmetry in the problem because the person who is sitting at the front here, stroke, will have their oar on one side of the boat or the other. So there's a symmetry breaking. Now think about the forces involved. When you sit here with your oar and you pull, the oar touches the rowlock and a force is exerted on the boat by the oar pressing on the rowlock. And like all forces, it can be resolved into 2 perpendicular components. One, the biggest, is in the direction that you want to go, down there. But there's a perpendicular component to that. And during the first half of the stroke, when the oar is pushing on the rowlock, that force is towards the boat. But in the second half of the stroke, it roughly reverses and is away from the boat. As you know, the oar is no longer really pulling on the rowlock. That's the recovery phase. And then you start the next stroke. So what happens is that for each oarsman, there is an oscillating perpendicular force that's for half a stroke away from the boat, half a stroke towards the boat. So let's work out the overall moment of those forces about the end of the boat. Okay? So if we just have 4 rowers, for simplicity, then let's work out the moment of that perpendicular force. Okay, so if S is the distance from the rudder, where I'm going to take moments from the end of the boat to the stroke, let's call that S, and then the other oarsmen are a distance r apart. So that inward force minus n times S plus n times S plus r minus n times S plus 2r plus n times S plus 3r. So in the first half stroke, that's the total transverse moment on the boat. And you notice all the S's cancel out, okay, because it's a balanced boat with the same number of rowers on each side. But there's a net transverse force of twice the force from any one oarsman on the rowlock times the inter-rower spacing. And for the second half stroke, n changes sign, and the moment on the boat is minus 2nr. So as each stroke is completed, there is this oscillating force on the boat, which will cause it to wiggle as it goes along, unless the cox counters it. Or if there's no cox, it's up to the stroke, really, to take countermeasures. So this is a waste of energy. If you could do without this wiggling force, you will go forward more rapidly. So the question is there another way of seating the rowers so that you don't have this constant transverse net moment? And so I tried to look at this systematically for any numbers of rowers. For the case of the 4, it turns out that there's one and only one way in which you can seat the rowers such that there is no transverse moment and no wiggle. And it's something that had been discovered experimentally in the late 1940s and early 1950s by the eventual Olympic gold medal winning Italian crew. And this is the configuration. So if you take moments about the end, this time minus ns plus ns plus r plus n times s plus 2r minus n times s plus 3r. You're already sort of seeing that this is an interesting little problem in finite series that will have a generalization. The s's never matter. You can set r equal to 1 and divide n off every term. And all you're asking is that if we take the numbers 1, 2, 3, 4 with 2 minus signs and 2 plus signs, how can we arrange them so the sum is 0? So it's a little problem in finite integer series. If we had 8 rowers, we'd have 4 plus signs and 4 minus signs. How do we combine them amongst the integers 1 to 8 so that we have a sum of 0? And you can prove all sorts of little theorems that it's only possible to get a sum of 0 if the number of rowers is divisible by 4, and so on. So this particular rig here, which is called the Italian rig after its sort of accidental discovery by the Italian crew in Lake Como in 1952, who set up their boat in this way early one morning when they were going to have to do a time trial, hoping that their coach would just call off the time trial because someone had been messing around with the boat. But he was rather annoyed to find the boat like this and told them that they were still going to have to row the time trial. And if they didn't beat the target time, 20 minutes later they were going to have to row it all over again. Well, not only did they beat the target time with this rig, they actually broke the course record on Lake Como. So they stuck with this rig, they won the European Championships and then eventually the Olympic Championships a few years later. If you move to 8, then if I apply the same logic, I found there were 4 and only 4 possible 0 moment configurations for our little idealized problem. Every row is assumed to be the same, and so on. So 2 are known, and the first one is just the previous example of the Italian 4 with another Italian 4 just glued on the end. So it's a series. There's another one here which sort of has an Italian rig in the middle and then the other 2 pieces at either end. And this was discovered by the German crews that dominated rowing after the Italians in the 50s and 60s. So Adam, their famous coach, really pioneered using this rig. But the other 2 rigs are new, okay, which had not been found before. And as you see, they're all just solutions of this little finite series problem. This sort of discovery caused lots of interest in the rowing world, and I sort of did interviews for the World Rowing magazine, and there were articles in Rowing Biomechanics about the details of this. You probably noticed that Oxford used a tandem one of these configurations last week when they won the varsity race. But they used one of the ones that were already known. I think it was the German one. And if we look here at the Olympic Games, I discovered after I'd done this that Canada used one of these rigs, again the German one I think it was, to win the gold medal in Beijing. But when we talked to their coach, he said he didn't do it for any of these mechanical reasons. He did it because they had some oarsmen who were extremely large. And by having this, I thought all oarsmen were extremely large, but this just gave some extra room for some people with some very, very long legs and arms not to run into other rowers. New Scientist sponsored some trials of the other two rigs, and if you're interested, if you look in New Scientist, you'll find there's a long article about it, and on their website there's a video and interviews of what happened with the Imperial College crews who tried out the other two rigs here. Here's the world record holder in the shot put, and this gentleman, Randy Barnes, is an American. He's put the shot 23.12 metres. He subsequently, naturally, banned for drug taking for several years. He still holds the world record for the shot, set a very, very long time ago. And most world records in these heavy events, particularly the women's events, really don't change for a very, very long time. And some of them people wonder whether they'll ever change, because the tests for drugs in heavy events are so much more stringent now. Well, let's have a look at the motion of a projectile like this. It's so heavy you don't have to worry about aerodynamic drag. And there are two surprises in this problem. Okay. The first thing, simple projectiles. Okay, at school you learn if you launch an object from the ground at speed v and you can treat it as a point particle and neglect air resistance at an angle theta, then this is the distance of flight, or the range. And if you want to maximize this, you want to maximize sine 2 theta, and you launch, therefore, when 2 theta is 90 degrees and theta is 45 degrees. Well, in practice, of course, shots are not launched from ground level. They're launched at some shoulder height of a very large man or woman who might well be 2 meters tall. Certainly when they extend their arm, they're going to be launching this object from 2 meters or so from above the ground. And so if you recalculate the range, allowing for this launch from above ground level, you're not going to get an optimal angle of 45 degrees. It's probably nearer 43 degrees, 43 and a bit degrees. And this is the sort of thing that you find in all sorts of elementary little articles in American Journal of Physics, or maybe even in Mathematical Gazette and other such publications, about how important it is to take this little detail into account, that you don't launch at 45 degrees to get the optimal range. Now, if you know anything about athletics, you know that top shot putters don't launch shots from anywhere near 43 or 44 degrees. The launch trajectory is much, much shallower. It's down around 39 degrees. So what's going on here? Well, the problem is in that all these previous analyses have treated the angle of launch and the speed of launch as somehow being completely independent, freely specifiable initial conditions. But if you've tried to lift anything heavy or to push it in the air, you will know that your strength is very, very different pushing things upwards to pushing things outwards or pushing things at an angle. So there's a great difference between the weight that you can push above your head and the weight that you can hold outstretched or that you can bench press. So if you look at some of the gym data, this is the typical experimental data for looking at lots of shot putters at the projection speed that they can obtain if they launch at some angle theta. And you can see that there's a definite systematic variation. So this problem of working out the maximum range is not quite so trivial. It's a constrained optimization problem. If you take this v of theta into account for the initial launch speed, then the problem you're interested in solving, what's the range against the projection angle, you've got a whole family of different possible curves here for different launch speeds, and you're interested in the maximum here. And the answer you get depends on how high a quality athlete you are, how large your V launch actually is. So for international athletes, you know, you're looking up at the 37, 38 degree type launch angle. So to get the right answer, to understand what's going on in the photographs of people like Randy Barnes, you've got to work just a little bit harder than simply projectiles being launched 2 meters from above the ground. Well, from throwing things to judging, and one of the most interesting collections of mathematical problems that sport has to offer are issues of scoring systems and judging. And if you want weird judging, then it's got to be ice skating. So my daughter is a professional ice skating coach, so I sort of get lots of information on the inside about all this craziness. Of course, the rules changed after the Olympics at Salt Lake City because something very outrageous happened. And I'm going to show you what that is. Well, actually, 2 things that were very outrageous happened. The second thing I'm not going to talk about was not to do with mathematics. It was simply cheating by judges. But what the strange thing was simply the appearance of a classic voting paradox of the sort that we understand in the mathematics of voting and economic preferences, actually emerging and determining the gold medalist in the women's figure skating. So there are probably some things that you don't know about skating scoring, or at least how it used to be. So you remember all those 6.0s and 5.9s that everybody gets very excited about. They don't count for anything. So if everyone skates and they get those scores are not carried forward. All they do is determine your position in that competition. So if you score 6.0 from every judge and the second competitor scores 2.0, you don't get any extra credit there except that you're first and they're second. So it doesn't matter by how much you were better than the second performer. So that was the first classic blunder that a mathematician could have told them not to do. So here's the situation in the Olympic women's figure skating, and these were the top 4 competitors: Kwan, American Hughes, and Cohen and Slutskaya. And the way it worked, you first of all skate a short program, and if you're the best skater with the highest score, they give you half a point. And if you're the second best, they give you 1. If you're third best, 1.5, and if you're the fourth best, 2. So it's as though they are using rankings as the score, but they halve them. So that when you do the long program, you get more credit because it's longer, it has more ingredients. So if you win the long program, you'll be given a score of 1.0. Then they'll add those 2 scores together, and the skater with the smallest score will be the winner. Okay, it all sounds very easy. But of course it turns into a disaster. So here are the outcomes from the short program, and then these 3 skaters skate in the long program. And after they've skated, the best performance is by Hughes. And so she's riding there with a 1.0, and the second best score is by Michelle Kwan, she's 2.0, and the third is the young American Cohen with 3.0. So at the moment, if we add the scores up, Kwan is in the lead overall. Hughes is second with 3.0. Cohen is third with 4.5. Slutskaya had been second in the first round. She then skates. What happens? So notice Kwan is ahead of Hughes. Okay? Well, Slutskaya skates and is the second best in the long programme. So that shunts Kwan down to 3 and Cohen to 4. If we add the scores up, Hughes and Slutskaya are now first. That degeneracy is resolved in skating by first taking the best performance in the long programme. So Hughes wins the gold medal because she was better than Slutskaya in the long programme. But look what's happened. Kwan was ahead of Hughes, but after Slutskaya skated, Hughes is now ahead of Kwan. So the performance of Hughes has changed the relative positioning of Hughes and Kwan. So this is a situation that usually in voting scenarios you tend to exclude by an axiom at the beginning. It's like the joke about the philosopher who goes to a restaurant and the waitress comes round and says that we have beef or fish, what would you like? And the philosopher says, I'll have fish. And then a few minutes later the waitress comes back and says, we've got an extra thing on the menu, we've got pork, would you like to change your order? And he says, yes, I will, I'll have beef. So this is the first time this paradox had sort of emerged and actually determined the gold medal in a high-profile event. And at root, the problem is one that mathematicians understand quite well. You mustn't add preferences. Okay, they're non-transitive. If you had kept all the 5.9s and the 6s and so forth, if you just added all those together over the 2 rounds of the skating, you would have got a far superior system of judging the results. So at root, the paradox that's happened here is simply that if you have 3 people and they want to decide amongst themselves which car we should buy. So they may be students, they're all putting in money. Somebody wants to buy the Audi A, somebody wants to buy the BMW B, somebody else wants to buy the Cortina C. And so they say, right, well, we're going to vote, each put down your preferences, and the first student's preference is Audi, then BMW, then Cortina. The second student is BMW, then Cortina, then Audi. And the third student wants the Cortina, second choice is the Audi, and third the BMW. So what happens if we look at these preferences? Well, the Audi is preferred to the BMW 2 to 1. The BMW is preferred to the Cortina 2 to 1. But the Cortina is preferred to the Audi by 2 to 1. So the preferences are non-transitive. You mustn't add preferences. And you'll recognise this paradox emerging if you sit in little academic and departmental committee meetings where you take votes on things. So the astute mathematical chairman will try to exploit this type of paradox whenever he or she can. Well, let's move on to a simple example of sort of probability and scoring. And this is a problem that you can deal with in a sophisticated way as you wish. This is the simplest way to do it. And it's really asking the question, is the Premier League in England just a random process? You know, do we need to go to all the expense and the trouble and the policing of actually playing the games? You know, could we just replace it by some simple algorithmic device? I mean, when the weather is bad, it's replaced by the pools panel. So why not have the pools panel every week and just run it in a random way? Yeah, so my wife thinks this is a marvellous solution and can't really understand why people haven't latched onto it before. Well, what happens in the Premier League? There are 20 teams and they each play all the other 19 teams twice. So they each play 38 games. If you look at football statistics, sort of in the large, over long periods of time, different countries, there's one pretty stable statistic. About 1 game in 4 is a draw. Okay, so let's assume that the probability of a draw is 1/4. And for simplicity, we'll apportion the remaining 3/4 of the probability sort of equally between home and away wins. So in any game, there's a 3/8 probability of a home win and a 3/8 probability of an away win. Now, we could, if we just had an 8-sided spinner, play all these games, sort of thing we used to do at school with funny little dice, and you could generate a random set of results, labelling your teams A, B, C, D or whatever for all 20 of them. Or you can put it on a computer and a few seconds later it will generate for you all the results and a league table where the team that randomly ends up with the most points we'll call team number 1. We don't have to call it Arsenal or anyone else, but let's call it team number 1. And so what you're seeing here in red is the randomly generated Premier League table from our simple model. Probability of 1/4 for a draw, 3/8 for home, 3/8 for away win. And when I prepared this slide, I just picked some past league result of the table. I just picked one where Manchester United didn't win, but Wolves were at the bottom, and they still are almost, aren't they? And what you notice about this, so up at the top here, this is all the usual suspects, Arsenal, Manchester United and Chelsea. The fourth team that year were Liverpool, who were actually closer to being relegated than they were to winning the league, even though they were in 4th position. And what you notice is that from 4 downwards, the random model really is a very, very good fit to the points distribution in the league. The top 3 teams, of course, are operating with a much higher probability of winning a game than our simple 3/8 at home and 3/8 away. I mean, Arsenal are winning 70% of the games they play that season. So this is a pretty uncompetitive league that year. Everything else here, you don't have to bother with most of these games. If you look more closely at this, you can see how you would make this model better. Down the bottom, the random model works pretty well. Up near the top, after the first 3, it's also pretty good. In the middle, it starts to deviate quite a bit. So why is that? Well, my guess, I think it's simply that if you're one of the top teams, it doesn't matter whether you're home or away, you win all the time. If you're one of the bottom teams, doesn't matter whether you're home or away either. You lose all the games. But if you're in the middle, you tend to win at home much more often than you win away. So our simple assumption of the same probability for a home and away win is not good. And that's what you would work on next to create a better model. Well, that's a simple example of scoring. Something that's a bit more sophisticated, if you look across sports, there's very complicated systems of scoring. You know, in the old days, in squash and volleyball, you only scored a point if you won a point when you were serving. So if you weren't serving, you'd have to win the next point to get serve, and then you would have to win again in order to score a point. The rules are changed now, and you get a point just for winning the rally, whether you're serving or not. So that's mathematically unfortunate because it was an interesting situation. In squash, there used to be a rule that if you were at 8-all and you were receiving, you could elect to play to 9 or to 10. So what should you do? Well, roughly you can see is that if you're not a very good player and you're really rather lucky to be at 8-all, you should play to 9. Because you might fluke 1 more point, but your chances of fluking 2 more are much lower. When you subject this little mathematical problem to a little bit of analysis, not entirely trivial, you find that if your probability of winning a point is bigger than 0.36, you should play to 10. But if it's less than 0.36, you should play to 9. But some sports like table tennis have changed their point scoring system recently. Well, I say recently, several years ago. If you play table tennis in the garage or at home, I bet you're still playing under the old rules. You're playing up to 21, best of 3 sets. But the real players, okay, the ones that don't play in your garage, the ones that are trying to win the Olympic Games, they play to 11. And they play best of 7 sets, and they just sort of have 2 serves rather than 5. So the rules were changed in this way to reduce the amount of time spent on long, rather one-sided games, and to reduce the effect of being the server, so that you didn't end up at 16 or 17 all, and then one of the players finds they're serving, and that really tips the scale so that they win the game. At Cambridge, we've had, I think she left a year or so ago, a year or 2 ago, we had the world's best ever table tennis player as a sort of master, PhD student. A Chinese woman who retired when she was 24 with 4 Olympic gold medals and I think 15 world championships, and was voted China's athlete of the millennium, I think, and was the deputy leader of their delegation at the Beijing Games, and I suspect might well be the leader in London. And she would occasionally, I think, play in and come out of retirement to play in intercollegiate competition or the local league. I never found anyone who'd even seen the ball, actually. So what one wants to know in games like table tennis is really what's the reward for skill versus luck? If you just played a game of table tennis with 1 point, okay, or if you just tossed the coin at the beginning, didn't play any points, okay, there would be no reward for skill really at all if you just tossed the coin. If you played just 1 point and the whole match was decided, again, if you're the weaker player, you've got a much bigger chance of just fluking that point and winning it. So the more points you play, the more skill is going to win out over luck. But you can't keep playing forever. So how many points do you need to play so that 2 evenly matched players will produce a result where skill will tend to determine the winner rather than luck? So let's take a simple model again. Suppose that you're playing a game like table tennis and the probability of winning a point is P. Okay? Well, you can go back and sort of change this to a slightly different probability if you're receiving or serving and so on. But let's see what happens if it's P. And let's suppose we're in top-level table tennis, so there's evenly matched opponents. Okay? So P is very close to a half. So we'll call it half plus a little bit S, where S is much, much less than a half. Then this is just like a series of sort of Bernoulli trials, of random trials, and if there are n, if you have to get to n points, where n might be 21 or 11 or something else, to win the game, then the probability criterion is that you want to win n points before you lose n points. And so you just work out the sum of the probabilities from the Bernoulli trials, approximate to the probability being close to a half, get rid of all the factorials using Stirling's approximation, and what you end up with is that the probability of winning n points before you lose n points is a half plus twice this little bias times the square root of the number of points over pi. So this is interesting. It has many features that you would expect. Okay, if S is 0, so they're perfectly matched opponents, then Q is a half also. But as S gets a little bit bigger than 0, so the chance of the n points being won grows with S. Okay, so the more games, more points you play, the greater the chance of skill winning out over luck. But the number of games, the number of points you have to contest goes like the square root of n over pi. So suppose that you're contesting each game by n points, so n could be 21 or 11, and then you're saying we'll play m games. Okay? So if it's best of 3, you need to win 2. Sorry, m is the number of games you need to win in order to win the whole match. So best of 3, m is 2. Best of 5, m is 3, and so on. Well, you need to apply this twice. So first of all, to win any one game, okay, your marginal advantage would be 2 sort of s dash, say, times root m over pi, but your s dash would be the 2s times root n over pi from winning the points in the game. So you fold those two formulae together, and your overall probability of winning the whole match, okay, is 4s over pi times the square root of m times n. Okay, so that's the key factor. So if you were playing under the old rules of table tennis, then n would be 21, and you would need to win 2 games, okay, best of 3. So m times n is 42. The change of rules, where you're best of 7 and you play each game to 11 points, m is 4 and n is 11, and the product is 44. So it's very interesting. You begin to wonder whether somebody who knows something about mathematical statistics had something to do with changing the rules, because the product of m and m are really very, very similar under the two systems. Okay? If under the new rules you paid best of 3, okay, m times m would be 22, and the reward of luck compared with skill would be twice as great as it was under the old rules. So you can use this type of consideration, all sorts of games, to evaluate the relative role of skill versus luck. Well, getting near the end, let's look at something to do with strength. So this little man, who's about sort of this tall, can lift 3 times his body weight. So I think he's been Olympic champion 3 times. It would have been 4 times, but he changed nationality and he couldn't compete. So Suleiman Oglu is a rather remarkable weightlifter. It's probably pound for pound the strongest person in the world. But weightlifting is one of those sports where there is rather meticulous categorization into weight classes. There are certain sports which don't have that, which you might have thought ought to. Shot putting we looked at earlier. You don't see many shot putters who are that big, and I think you can guess why. You won't get very far if you're a little shot putter. Another sport I was investigating in the last week, I discovered something interesting, is in the Paralympics, the wheelchair racing really ought to have weight classes. The dominant source of resistance for the motion at all distances is rolling friction, which is directly proportional to the weight being carried. And although there are meticulous regulations about the sizes of the chairs and the diameters of the wheels, there is none about the weight of the wheelchair. And the wheelchairs vary by at least 10 kilograms from competitor to competitor, and the competitors' weights vary enormously. And so there is an enormous difference between different competitors' total weight. And that really is the deciding factor about how fast they go. Well, what about strength? How does strength change when you get bigger, when you get heavier? Well, strength does not change at the same rate as volume. Strength changes like a surface area, not as a volume. And you can understand that if you want to snap something like this piece of wood here, when you break it, you have to break through the molecular bonds in a cross-sectional area through one point. And I won't find it any harder to break those bonds at this point if this is a mile long or if it's just a metre long. So the total weight of this ruler, the total volume, is not relevant for how much strength is required to break this little slice of molecular bonds. So the strength of a material like that depends on a cross-sectional area, something with dimensions of size squared. And You've probably seen these familiar examples wandering around your home. The weight of something that grows, like a cat, grows like the volume, which is some measure of the size cubed. And you notice that strength does not grow at the same rate as R increases as volume. So when you have a little kitten, it's strong enough to hold its tail bolt upright like a spike. But as it grows into a bigger cat, the strength of the cat does not scale at the same rate. And so its tail tends to bend over. It's not strong enough to suspend its tail in that same way. So what you can see from these two things here is that strength is proportional to weight to the 2/3 power. So this is rather crude and simple. We could have done a lot better here if we wanted to. But what it tells you is that if you try to scale up on the same body plan, eventually you'll break. You won't be able to support your weight. So you can't have a giant the size of the Empire State Building. It will not be strong enough to support his weight. But this simple insight tells you you might be able to understand the world weightlifting records just on the back of an envelope. You see, the strength of a weightlifter is the weight lifted. And if we know the weight class that they're in, and they're very narrow, this simple rule ought to tell us how the world weightlifting records vary with the weight of the lifter. And if we do that, we really do quite well. So I've plotted weight cubed against weight lifted cubed against square of the weightlifter. So this is the 2/3 law that we were just looking at. And you can see that really there's a pretty good agreement. Okay, weightlifters do some quite sophisticated mathematical things in trying to scale the performances of different weightlifters to the same sort of numerical coefficient. And to do that, they have to introduce a rather more complicated weighting for what happens with these very, very big, super strong weightlifters. Because these guys up here, the people that weigh about 30 stone, they don't tend to follow this rule. They're the weakest, relatively. If they did, they would break. And so you want to try and take that into account. But you can see, looking at a picture like this, you can decide who, kilogram for kilogram, is the strongest of all the weightlifters. But it's rather gratifying that this very simple proportionality allows you to understand what's going on. And it would also allow you to understand, if you looked at shot putters, of different weight, you can understand how their strength varies with their weight, and therefore how the launch speed is going to vary and how far they're going to throw. You can understand what the marginal advantage is being a giant shot putter as opposed to being a small one. And whether the shot putter of normal size throwing a little bit less might be actually intrinsically a superior performance. Well, finally, what's the maddest sport of all? So sixth formers and students are always interested in, what's the most extreme human experience that you can have? And if you ask people, they tend to think it's being an astronaut, it's being launched in the space shuttle or at Cape Canaveral or something like that, or being a high-performance fighter pilot. Actually, it's none of those things. The most extreme physical experience that anyone has is being a drag car racer. So the accelerations here are quite extraordinary. So you know how drag racing goes. It's over a 1/4 of a mile course. The winning times in the top races are about 4 seconds. Okay? So start from rest. Just to get a perspective, suppose you're in your drag car on the starting line at rest. Michael Schumacher comes past in his Formula One car at 200 miles an hour. You start from rest. You still beat him to the finish. So the accelerations are quite extraordinary. 6G, and health and safety is very problematic. So detached retinas are almost obligatory here. The deceleration is even more of a problem. Parachutes are thrown out the back and you decelerate very, very rapidly. You're also at the risk of serious ear damage if your muffs should fall off at all, or if you're watching. So the sound levels are extraordinary, and you're sitting in effect on an enormous tank of rocket fuel. Probably a large fraction of the total mass is this rocket fuel. So you get the general idea. This is, not really Sunday driving. It's American, that's why. But it's an interesting little mechanics problem. It's sort of problem that you don't see at school or undergraduate level. It's motion at constant power to a very good approximation. So if we just neglect the little bit of rolling friction at the beginning, which we can take into account if we want, that what's happening is the power, which is the force times velocity, which is mv dot times v. We'll forget about the changing m. You can add that in if you want. No problem, it still solves. And this is just a half m, missed out the m there, d by dt of v squared. So if the power is constant and you start from rest at t is 0, from x is 0, the square of the velocity is proportional to the time. Integrate again, the distance you travel in time t is given by this 3/2 law. And interestingly, if you turn this around as an expression for v in terms of x, you get this rule of thumb that turns out to have a name in the drag car business when numbers are put in old-fashioned units, and it's called Huntington's rule, which was just a sort of engineer's rule of thumb telling you what speed in mph you're going to get if the power of the car in horsepower divided by its mass in pounds is given by this. And this factor here, which we can calculate, is about somewhere between 270 or when we calculate we get 270, it's observed to be 225. Discrepancy is because we've been a bit idealistic. If we take into account that there's a small period of initial motion which is dominated by the frictional force, okay, which is just coefficient of friction times the weight, okay, this period will end when half mv squared becomes equal to the frictional force times some distance, and if we just work out where that's true and then put that distance into the velocity rule, we've got a new initial condition for the motion at constant power from that position. And that gives you the right answer. So it's a rather nice little mechanics problem of a different sort. And if you want to allow the mass to be a time variable, you'll find it also solves exactly. And you know the fraction of mass that's lost in this problem, so you can put it all together. Well, I think my time is just up, and I hope that I've given you some flavour for a lot of different places where there's often quite simple mathematics which can give you insights into what's going on in sport that you might not get in any other way. And if you're a competitor, you might even think that there might be something that you could learn to your advantage. Thank you.